Yeah, they're from the church. Yeah, they're from the Church of Jesus Christ of the Latter Day Saints. They'll come back. Unfortunately, yes. Sadly. You're right. I don't recommend it.
What do we mean by you agree with A? Okay.
Not
Uh, did you deal with the 1/4 or did you pull them out front?
I deal with them.
Much easier if you pull it up.
I like cross that bridge. I like what? You have to prove to me that you're not. I need to eat for
Yes. Okay. All right. So that converged. It did converge to a sum of a 4. Yes. Okay. Moving on to today's lesson, P series. If you've been doing as I asked, and you did a geometric series, you identified it first and foremost as a geometric series before you did anything else. So for example, in that problem, you would start by saying, hey, this is geometric because there's this exponential thing, and then you go and do your thing. It wasn't crucial that you did that before because you didn't really know that many series. Now you'll know one more, and giving you a total of 3, telescoping, geometric, and P-series. And it'll be more important that you identify it first in your work. All right? So, what is a P-series? Well, let's build off of what you could call a P-integral, but it's not really a P-integral. There's no such thing. But that integral that we've been dealing with, that improper integral, change that to 1. That's doubly improper. I don't want to even go that vertical asymptote. So that improper integral, that would converge under certain conditions of what P is a constant and diverge under other constants for P. What do you reckon the great dividing line is? When P is 1 is the great dividing. All right, so let's go if P is less than 1. Let's say P is a half, just to illustrate the point. Then I'll gradually get to the series idea, okay? If I were to do that, then the problem would become 1 to infinity of 1 over root x. You follow? If P was a half, then the power is a half, which is the same as square root. This is a nice review. We know that is to be written as a proper integral with a limit. And I would also probably write that as a power, so I integrate it without mistake. If I integrate that, x to the negative 1/2 by power rule becomes 2 root x. Now that is the limit as a goes to infinity of 2 root a minus 2, and that then diverges, because as a gets large, the result gets large. Infinity minus 2 is still infinitely large, okay? All right. If P is 1, then it becomes more like 1 to infinity of 1 over x to the first, which is the same as the limit as a goes to infinity of 1 to a of x to the negative 1, or 1 over x. What's the antiderivative there? Natural log. It's not a power case. It's that rare case, a power ending in natural log from 1 to a. And natural log of a. As a goes to infinity, the natural log of a goes to infinity, and therefore that diverges. If, however, we have a little bigger power in the denominator, say P equal 2, or even, actually, let's go P to the 1 and 1/100, or 101 hundredths. Just barely beyond 1, okay? Then the problem becomes something like 1 to the infinity over 1 over x to the 101 over 100, which is the limit as a goes to infinity from 1 to a of x to the negative 101 over 100. Now that great dividing line of 1 makes all the difference, because when you integrate that, it's still negative, and therefore in the denominator. What's the antiderivative? When you raise it by 1, it becomes x to the negative 1/100. X to the negative 1/100 divided by negative 1/100 is times negative 100 over 1, I guess, if you like. I don't know what I was thinking there. But the key is that it still stays in the denominator. Even after raising it by 1 power-wise, it's still in the denominator. And so if I take negative 100 over x to the negative 100, first of all, because it's negative, it's in the denominator. And because it's a fraction, it's a root. So x to the negative 1/100 means the same as x to the 100th root in the denominator, right? So that's the 100th root of a plus 100 over the 100th root of 1. You see? Now that said then, if a goes to infinity, this guy goes to 0 and it converges. So 1 is the great dividing line. 1 or less diverges. 1 or more than 1 converges. Now, this is a big idea, what's called the integral test, which is in tomorrow's lesson. But we'll start by saying this. Integrals and series are similar because, why are they the same? Similar, not the same, similar. They're sum of infinitely many. Beautiful, that's calculus, okay? They're the sum, they sum infinitely many. They're different because what they sum is different. And when I add a series, I'm adding all these little dots to get a sum, okay? When you do an integral, you're taking little dx's times that value and getting an area, and then a little area and a little area. You're not finding the same thing. They're not the same, but they are similar in that they are adding something tied to the same function, but they're different because what they add is different. These are just finite numbers versus tiny thin areas, a little more going on in an integral than just what's the function at whole numbers. The area under the curve is at infinitely many numbers, even in just from 0 to 1, whereas in a series, you're just talking with whole numbers. So there's finite versus infinite, and real versus, continuous versus whole, and so on. So they're similar but not the same. Here's the deal, though. You could prove, though, that this series that is like that integral we just talked about behaves exactly the same way. This is a p-series, right? Instead of x in the denominator, like we see in an integral, in series we deal with n, representing whole numbers only, right? And instead of a finite sum, sigma, we're talking... sorry, when I say series a lot, it tends to think I'm talking to series. So this will happen all so much. So anyway, here we go. So this is a finite versus infinite, but they behave the same. Now this, a p-series, is one where you have 1 over n to some power. And it depends on what that power is as to whether it converges or not, but it behaves just like the integral we talked about. This p-series will converge if p is greater than 1. And it'll diverge if p is less than or equal to 1. The one where the power is 1 is one of the most famous series there is. 1 over n is called the harmonic series, and it is a big one. Okay? You will then sometimes be asked to use this logic to prove something converges or diverges. That's pretty common. So this is what book problems will look like, and then we'll talk about what AP problems will look like. The question might be something like this. Does the series converge or diverge? Justify. Now, you could, just like geometric, it is not bad to start with the divergence theorem, which is to say, does it even have a chance? Do the terms go to 0? Yes. So does that mean it converges? It means it might converge. Now, if, however, it's a series that you are familiar with, and you can go more specific than just this big idea, does it even have a chance, then it is okay to bypass that, say, all right, I could prove it has a chance, but I recognize this is a p-series, and I'm going to go to case specific. The first thing I would like you to do is identify the series. This is a p-series because it's 1 over n to a power. Then show the p-value and the test. Okay, so by that I mean something like the great test value is 1. So you're saying, how does it fall on either side of 1? In this case, you'd say for this problem, P is 3, which is greater than or equal to 1. And therefore, we conclude converge or diverge. Based on that evidence, we would say converges. Oops. Greater than, sorry, my bad. Greater than 1, and therefore it converges. Okay? If it's greater than 1, it converges. If it's less than or equal to 1, it diverges. Try one on your own. How are we doing? This is a P-series with P equal 3/4, which is less than or equal to 1, which diverges. Okay? That's exactly what the work should look like. I mean, there is nothing to be left out. If you say just that, that won't do. If you say the P is less than or equal to 1, you guess what the P is, that won't do. Okay, you must have everything I have there, or it is incomplete. Is that understood? Okay, it is important that you understand that mixtures of series are not one or the other. For example, if I had this 1 over n times 2 to the n, that is neither a P-series nor geometric. It is not either one. Okay, this is not geometric or P-series. So that you would run a totally different test. You'd probably use the ratio test, but that's for later. Okay. Let's see what a little bit of. Actually, could you throw one small thing into your notes, just in terms of using the vocabulary? One more, just like this. Does this series converge or diverge? And this is special in that you could go super specific, and I would take either one. You could still do P-series like you've been doing. Say P is equal to 1, and that's less than or equal to 1, so it diverges. But if you recognize this is the big boy, then this is, you could also say this is the harmonic series, and the harmonic series diverges. That is an accepted fact. It's been proved 100 million billion times. Yeah, so that's also acceptable. That's specific as it gets. All right, you with me? Yes, hit me.
Why? You have like a note on here that says you rarely find what number it converges.
Oh, yes.
Why?
Good question. All right, so on a P-series, there is no formula for what it adds to. It doesn't, there's no, it's not like geometric where you say, now you find the sum. You don't do that. On a harmonic series or harmonic divergence, but on a converging P-series, you don't find the sum. You just say it converges and call it good. Okay, it doesn't, there's no formula. The best you could do is approximate it with a really large partial sum and call it good at that. Okay, take a look at this bad boy. Try this one. See if you can get it on your own or with your math amigos. It's actually really easy. How are we doing? How would you write this formula for that? Yeah, there's no one over it. What's going up by one each time and therefore the end? The base is what's going up, and so that's the end. X is the power, which we're supposed to find. Okay? That's a p-series, kind of. Why isn't it a p-series? Okay, so how could we make it look like a p-series? Then I would say this converges if the power negative x is less than 1 or greater than 1? Greater than 1. And that implies that x is less than negative. Okay? All right. Try the next one. Thank you, Paige and Katie. Do you have a chance to do that next one? I don't want to rob you of the chance to do it yourself. Good? Okay.
Oh shoot, I had it backwards.
Okay, how we doing? So, A, I look at it as 1 over n squared. You don't have to do this, by the way. You will get better and better at looking at expanded form and seeing it too. But right now, you probably are better if you're in sigma notation. Do you agree that the first is a p-series?
Yes.
And p is 2. And therefore, this converges. The second one is the harmonic series, and the harmonic series diverges. And the last one is a p-series? Is a geometric series. What is the, I don't know if this would be necessary if I really wanted to find a sum. You might be able to look at this and say what the R is. What is R?
R is
Negative 1/3. Does that meet the conditions for convergence of geometric? Yes. And so we would say 1 and 3, and our answer is C. Try the next one, please. What do you say? Greater than 3. Okay, and this is one of those that students feel like, I could do it all mentally. I should be able to do it all mentally. Sometimes you can guess it and fine. But me, you gotta know yourself. Me, I cannot do it mentally and succeed 100% of the time. I could succeed 2/3 of the time or so. All right. Yes. Yes. You have to deal with that, guys. So I'm cool with k plus 1 times a half.
I didn't notice that was there.
Yeah, you have, it's part of the equation. Yeah. So if you did half k plus 1 minus 1 is greater than 1, cool. Yeah.
But what if there was no x?
Then that would be fine. You bet. You bet. That maybe you could do mentally. Yeah. All right. And would you do? Is this a problem somewhere? Would you do 2, please? If this is somewhere, I don't. It's on there. Okay. I don't know if I have a next slide. Okay. Actually, I just let you work at your own pace. Do the rest of them, please, and we'll go over. Or would you rather go one by one, or just do them all? One by one. Okay, let's do one by one. What series is that? What? Feels like it's geometric. Tangent of 1 is a constant, 2 a power. It's geometric. Actually, I should be able to do that without. Is that positive or negative? 1 radian is about 50 centimeters. So it's definitely positive. This is greater than. Oh, it's got to be greater than 1. And I don't know if it's greater than 1 or less. Oh, yeah, I do. 45 degrees is 1. So that's greater than 1, yeah? Tangent of 1 must be greater than 1, isn't it?
Yeah.
That's greater than 1, so it diverges. Okay? All right, try the next. A little different notation here. You're getting some good practice with different textbooks notations. ¿Listos? Ready? What's the sum? Or does it diverge? Diverges? Sydney? Diverges? Lily? Does not diverge, it converges. To 1/3.
Oh, I heard the first time.
Okay. First of all, this is not the term formula, it's the partial sum formula. It's not a sub n, it's s sub n. And you're taking the limit of that partial sum formula. These, what do these go to? Lie in behavior. 1. And this is like 3 to the n, 3 to the negative 1, over 3 to the n. This goes to 1/3. Okay, please don't mistake S sub n for A sub n. That is a partial sum formula, not a term formula. Now, if they said that's A sub n, well, you're good. It diverges, but that wasn't the question. All right. Try, yeah, this one. How would you approach this? Let's not do it because it's too much. How would you do it?
We don't have that.
You don't? Oh, good, because it's a mess. It's telescoping plus geometric. You wouldn't love it. All right. How about the next one? Try the next one. What do you say? It is it. Okay? That's the thought process. All right. Last but not least, those two. Give me a quick justification off to the side as well, please. Go, go, go. What's the series we're looking at there? 1 over n cubed. P series equal 3 is greater than 1, so converges, yes? What about the next one? Is it a P series? What is the power? 2/3. Yes. That is a P series with? Okay. P equal 2/3 is less than or equal to 1, so it. All right. Okay, cool. That's that. Question on 126. 25. 14. Okay. Let me know if you have more later. though? All right. The odd function should tell you two things. What does it tell you? Okay, it's symmetric about the origin. Could something be symmetric about the origin and have a y-intercept of something besides the origin? Nope, not a continuous function anyway. So the fact that it's odd tells you D is 0. It actually also tells you that B must be 0. B cannot be there for this to be an odd function. So that's a no. B is an even power. It must be 0. That's a little known fact, and if that's something, I can see why. But the idea for even or odd, besides all the pre-calculus stuff, is that if a function is odd, its derivative should be even. If its derivative is to be even, then that B cannot be there. So, that said then, I have now that P of x is x cubed plus cx. Now this q stuff, I assume that I am not going to be able to find a real c. Am I gonna? Is this some kind of q-ish number?
Yes.
Oh yeah. Okay. If it has extrema there, that implies that p prime at q is 0 or undefined. But because this is a polynomial, it's not undefined. It's just 0. So 0 equals q cubed plus c cubed. So c is something.
Wait, I mean, you have to take the derivative first.
Oh, I never took the derivative. You're right. My bad. Thank you. Thank you. Yes. P prime is 3x squared plus c, and therefore 0 when q is put in for x. And so c feels like negative 3q squared. Or would it also be, I guess it wouldn't matter if it's positive or negative q, it's odd. So c has to be negative 3q squared. Is that right? Kind of weird. Okay, well, that's good enough for me. 14, is 14 it? Yes, the question?
Yeah.
Okay, 14. The fourth partial sum. I don't know if I said if you had to use your calculator, or you could use your calculator, or you could do it by hand, but it's not too bad to do by hand, I think. Does it start at 1? Nope, it starts at 2. Okay, so first of all, make sure you understood it started at 2, not 1. The fourth partial sum is the sum of the first 4 terms. It does not mean through n equals 4. No, it means through 4 generated terms. So when n equals 2, that's the first term, 4 over 4. When n equals 3, that's the next term, 9 over 8, right?
Oh, that's forward.
Okay, 9 over 8, and then 16 over 16, if I'm not mistaken, and then 25 over 32. And then I don't see why you need your calculator to do that. I assume you can get common denominators and add fractions still.
Yeah, just
Okay. Other question. Okay, cool. Right on. Just enough time. Super duper.